Okay, so basically implicit differentiation is similar to what we've been doing before. It's the exact same method in some sense, but now it involves two variables. So generally it's like an equation of a circle, could be something that we're required to differentiate implicitly. So we have two variables, an x and a y, whereas up to now all the ones that we have differentiated have been maybe something like y is equal to 3x to the power of 4 plus 2x cubed plus x plus 5. Okay, so that's something that we've differentiated, or we might have differentiated y equal to x times sine of 3x over 2 or something like this. Whereas now, so all of these had one variable written in terms of another. This one we have two variables. So let's look at a couple of questions and a couple of ways to differentiate implicitly. Okay, so here we are given an equation of a circle and we're asked to use differentiation to find the slope of the tangent to the circle. So here we have our equation x squared plus y squared is equal to 25. Well, if I was to differentiate that normally, well, x would go to 2x. Y, well, same principle. So multiply by the power and reduce the power by 1. And then we also have to incorporate here, because it's in terms of y, it's dy dx. And 25 goes to 0. So now, in order to solve for this, we want to get dy dx on its own. So what am I going to do here? I'm just going to bring over my 2x to the other side. So I have minus 2x on both sides, so they cancel, and we have 2y dy dx is equal to, well, 0 minus 2x is minus 2x. And then just to tidy it up here, so we're going to divide this side in order to get dy dx on its own by 2y, so here by 2y. Again, these two cancel, and we have dy dx is equal to, and our 2's can cancel there, so minus x over y. So that is the differential of that circle there. So that's going to be, and now we just need to sub in at this point here to find the slope of the tangent at that point. So we'll just finish off that part here. We have dy dx. And to show that we're just doing it at that point, we draw our little line and we put in here 3, 4. And that's equal to, well, this is x and this is y. So that's equal to minus 3 over 4. And that's our answer there. We don't have any further work to do with it. Okay, so let's look at another using this same method. A similar type question. So here again we're given another circle and we're told the equation of the circle is x squared plus y squared minus 6x minus 2y minus 3 equal to 0. And we want to find the slope of the tangent to that circle at the point 54. So let's differentiate it first. So here we get 2x. We also get our 2y dy dx. So every time we differentiate y with respect to x, we have to include this part here. So minus 6 minus 2 dy dx, and 3 goes to 0, so that's just equal to 0. So now we want to get our dy dx's on their own. So we're going to group those together and push everything else over to the other side. So I want to get rid of minus 2x on this side, and I want to get rid of the minus 6 on that side. So here I'm going to say minus 2x plus 6. So they cancel, and this cancels. So now I'm going to have my dy dx. I'm going to just write that in red here because I have it underlined in red. So that's bracket 2y minus 2, and that's going to be equal to minus 2x plus 6. So now in order to get dy dx on its own, Here I'm going to divide simply by 2y minus 2. And so I will also divide here by 2y minus 2. So these cancel here, and we have dy dx is equal to minus 2x plus 6 all over 2y plus 2. Well, we can see that 2 is common to all of those, so let's just simplify this down and say dy dx is equal to minus x plus 3, and that will all have been multiplied by 2 all over 2 times y plus 1, and so there our 2's cancel. And so our answer then is, so dy dx is equal to minus x plus 3 over y plus 1, and that of course is our slope to our tangent anytime we differentiate. And so we want to find that at a particular point, so let's do that at the point 5, 4. So here we have dy dx at our point 5, 4, and that's equal to minus 5 plus 3 all over, and y is 4 plus 1. So here we have dy dx at the point 5, 4 is equal to, well, minus 5 plus 3 is 2, minus 2 in fact, and 4 plus 1 is 2 over 5. So that's the slope of the tangent to that circle at the point 5, 4. Okay, so this is the strongest method for solving implicit differentiation, but I'll show one alternative method in the next example. Okay, so another method is just to get it all in terms, to write this equation now as y in terms of x. So we could have here, we're starting off with x squared plus y squared is equal to 16, and so y squared is equal to 16 minus x squared. So y is equal to the square root of 16 minus x squared. And just to make things easier for ourselves, we can write that as y is equal to 16 minus x squared all to the power of a half. Now, so this method is fine for an equation like this, where we didn't have any 2x and 2y, or, you know, it was just a nice simple equation. But so now that we have this, we're just going to simply use our chain rule in order to differentiate. So y is equal to v to the power of a half, where v is equal to 16 minus x squared. So here we have dy dv is equal to a half v to the power of minus a half, and dv dx is equal to minus 2x. Tidying up then, that gives us that dy dx is equal to 1 over 2, and v we said was 16 minus x squared to the power of a half, and that's times minus 2x, and that would be the same as being over 1. So I can see straight away that the 2's cancel. So and here I have, so dy dx, and the thing with implicit differentiation is we want to have it expressed in terms of x and y at the end. So at the moment I just have x's here, so minus by minus x, or 1 by minus x is minus x, and here 16 minus x squared to the power of a half. Well, what is that? That was this bit here, wasn't it? So 16 minus x squared to the power of a half is y. So that's our answer there. Now, we don't need to know this method. The other methods that we've done in the last two examples will suffice for this type of question as well. So this is just to have as a backup. Okay, but obviously this method can't really be used in the longer type equations. If we had an equation that said, for example, x squared plus y squared is minus 4x plus 8y is equal to 24. We're not going to solve that using this method here. It's too difficult, too time consuming. Okay, so there are two methods, and I'll put some work up on Schoology now. Okay, so let's just make sure that you have all these notes down in your copy. Thanks.